let the function f be a real function. This is differentiable on open interval. Then f is convex on open interval a comma b if and only if its derivative f dash is increasing on open interval. Now proof. If and only if condition, then we have to prove that it is necessary condition and sufficient condition, and the function is given differentiable. We have to prove the convex if the derivative exists. Now firstly we said that the function is convex. Let this, then x1 is less than 2 x2, x2 is less than 2 x1, x3 is less than 2 x2, x3 is greater than 2 x2, and x4 is greater than 2 x3. The by convex function theorem, f of x2 minus f of x1 upon x2 minus x1, which is less than x equals to f of x3 minus f of x2 upon x3 minus x2, and this term is less than equals to f of x4 minus f of x3 upon x4 minus x3. Now let x2 is converging to x1 plus and x3 is converging to x3 plus, then this implies that f dash of x1 which is less than equals to f dash of x4. This shows that f dash is increasing. Now we let sufficient condition. For sufficient condition proving let f dash is increasing. F dash be increasing on open interval a comma b. Let x1, x2, x3 is in open interval a comma b such that x1 is less than equals to x2 and x2 is less than to x3. By mean value theorem, what is that? F of x2 minus f of x1 upon x2 minus x1, which is f dash of c, and c is in between x1 to x2. F of x3 minus f of x2 upon x3 minus x2, which is equals to f dash of p. P is in between x2 to x3, right? Since f dash is increasing, so this implies that f dash c is less than equals to f dash of p, right? Thus f of x2 minus f of x1 upon x2 minus x1, which is less than equals to f of x3 minus f of x2 upon x3 minus x2, hence f is convex.